Okay, folks. All right. Let me take one first. Let me ask those of you out there in Zoom, can you hear me? Please say something or type something just to let me know that. Okay. How about you, Miss Mohammed? Okay, good. All right, folks. Oh, wait a minute. I think I know what just happened. So, if there's any issues that you guys out there in Zoom might experience a result of some lagging, I apologize. That's not working. So basically, going directly from my laptop in order to carry this. So I apologize beforehand. Make sure that I'm recording this lecture so that you guys will have access to it afterwards. So, we continue from where we left off last time, in chapter 2. Again, just like the previous, classes so far. So, let's review of what we have learned before. So now we're going to talk about subatomic particles. And as you all know, basically there are three major subatomic particles. You have the protons and neutrons, which are located in the center of the atom, which is called the nucleus. And then surrounding the nucleus, you're going to have electrons. All right, as stated here, they're dispersed around the nucleus. And this table here basically summarizes the different type of subatomic particles and their properties, right? So as you can see here in this column, it gives you the relative approximate mass. And what you see here is that protons and neutrons are basically equal to each other in terms of mass, but electrons are much lighter to the extent shown here, all right? And then in terms of the relative charges that the particles carry, neutrons, of course, neutrons therefore have no charge, and electron carry -1 charge. And in terms of the location of different particles within the atom, as we said before, the protons and the neutrons are located in the nucleus, while the electrons are located outside the nucleus, all right? Another term that you guys should be familiar with is this term right here, isotopes. These are atoms having the same number of protons, but different numbers of neutrons, all right? And at this juncture, we need to define what we mean by the atomic number, which is the number of protons in the nucleus of a given atom or a given element. And as such, each element has its own unique atomic number, right? So for example, sodium is the only element that has an atomic number of 11, which means that it has 11 protons. Another one will be iron. Iron has an atomic number of 26, which means that it has 26 protons, all right? The mass number is the sum of the numbers of protons and neutrons in the nucleus of an atom, all right? Now, please, and I had to say this to my group last time, my intro group last semester, and I'm saying it now, please do not confuse the atomic mass, right? The mass number is the definition given here. It is the sum of the number of protons and neutrons present in the atom. The atomic mass is, as the term suggests, the weighted average mass of all the isotopes of the particular element, right? And so if I just highlight one example, carbon, right? If you look at any legitimate periodic table, there are two numbers associated with carbon. The 6, which would be the atomic number, which represents the sum of the number of protons and neutrons present in the atom. And then you have 12.0, depending on the periodic table, 12.01, which represents the atomic mass. That is not the mass number. Please do not confuse the atomic mass with the mass number, all right? So, based on the atomic number and based on the mass number, we can easily calculate the number of neutrons by finding the difference between the two, right? So the mass number minus the number of neutrons would be equal to, the mass number minus the atomic number would be equal to the number of neutrons, all right? Okay, some other things about isotopes. There's a shorthand way of representing isotopes using this symbol right here. Now, conventionally, we use A to represent the mass number, generally speaking, and Z to represent the atomic number. So basically, we can use this sort of symbol. In some textbooks, they call it the isotopic symbol. Let me write this down. Oh, it's not to take over. Let me do this. So where's pen? Okay, looks like this connection is working. Let me see if this works. Right, everything is going to malfunction right now at this point in time, so I might not be able to write down anything. Anyway, so this symbol here, we call it the isotopic symbol, right? Where A is the mass number, is written as a superscript up here, then Z would be the atomic number, which is the subscript right here, and E represents a symbol for the element. So therefore, when you see this, you can easily tell that we're talking about chlorine, where the mass number is 35, the atomic number is 17. And here we have an isotope, another isotope of chlorine, where the mass number is 37. Everything else is the same, right? So based on these symbols, we can answer some questions, like, for example, how many protons are in chlorine 35? And the answer is? Exactly, 17. Next question. How many protons are in chlorine 37? 17 again. And then another question, how many neutrons are in chlorine 37? Okay, right, 17 gives you 20. Okay, good. All right. So here's another example. How many protons, neutrons, and electrons are in green basic one atom? In this case, you notice that they did not do identical. But no worries, right? All you have to do is vertical and identify the atomic number of bromine. So if you consider vertical, you see the atomic number of bromine is 35, right? So automatically that gives you the protons. And let's again, and all the neutrons are 1 minus 35, whatever that gives, all right? Then all vectors do what? We'll get all vectors. Because in a neutral neutrons, it is the same. Okay, so let me move on to something I mentioned before, the atomic mass. Now, as you all know, atoms are very, very small, right? So we cannot use the conventional units of mass that we use to measure or express the mass of regular size objects, right? So somebody decided to come up with this called atomic mass unit, AMU, and by definition, 1 AMU equal to 1/12 exactly the mass of a carbon-12 atom, right? So whatever the mass of a carbon-12 atom is, 1/12 of that exactly would be equal to 1 atomic mass unit. And it turns out that that unit equal to 1.66 times 10 to the minus 4 mass, right? So 1 atomic mass unit is equal to 1.66 times 10 to the minus 4 grams. And one thing I mentioned here, which might become counterintuitive, that in an atom, if you have all the protons, neutrons, and electrons in terms of their masses, it turns out that the sum total of the mass of those particles in the atom, the sum total of the mass electron, is not exactly equal to the mass of the protons, neutrons, and electrons in the atom. Now, I won't go into the reason why, because later on. Chemistry, then you're going to see the reason why that is the case, right? Even though at first blush might seem a bit confusing. All right. Okay, so continuing our discussion about the mass. Question: all isotopes elements have the same mass and as well? No, because of the difference, right? So what you'll find is that the universe, for one particular element, or for any particular element, what you'll find is that you find some atoms which are heavier, right? Factor element, and then other atoms lighter. And basically, what we find also is that there is a relatively fixed percentage of different types of isotopes that exist in the universe for different elements, right? So one point of the example of carbon, carbon A acid carbon carbon 12, right? In fact, if you have any sample that contains carbon, 9.892% right? And the rest will be carbon 13. In fact, you also have carbon 14, which is very trace amount of the present, right? Flow just will be concentrating on these two elements, these two isotopes, so flow and carbon first. Now, this is where I really appreciate this because so basically I need to show you how to see things are electrical elements. Let me try some. Okay, I don't know what I'm gonna do. Maybe I'll just try to write with mouse. I know that doesn't work out too well, so. Okay, so let's see here. All right, so here we have carbon 12, carbon 13. Here we have what we call the relative or percent abundance, right? So basically what this is saying is that in any sample of carbon or any sample containing carbon, 98.892% will be carbon 12, 1.108% would be carbon 13, and this would be the fractional abundance. And of course, obviously, you get this by simply dividing each of these by. So here's a question being asked. It says, use the data cited above to determine the weighted average atomic mass of carbon. Oh, that's it. So you're to determine the weighted average atomic mass of carbon. And it gives you some further information. It gives you that the atomic mass of carbon 12 is 12.00000 AMU, and for carbon 13, its mass is 13.00335 mu, all right? So based on the information given, plus the information given up here, the question is asking for you to determine the weighted average atomic mass of carbon. So the way you go about this is, I'm going to start off with carbon 12. I'm going to write down the fractional abundance of carbon 12, which is 0.98. Calculator. Okay, so let's see here, 0.98892 times 12. And according to my calculations, this works out to be rounded off. Now, in this case, I have to round off to 5 sig figs. So this is going to be 11. Six. So fractional abundance is 1 So 0.0118 times 13.00335. And according to the calculation, again rounding off to 4 sig figs, I would get 0.44. To get the final answer is 0.867 plus 0.1441. So I would have to round off to 3 decimal places. And when I do that, I'm going to end up with 12. What you'll observe in the periodic table for the atomic mass of carbon-12, right? In fact, all the atomic masses that you see there in the table basically is obtained by doing this type of calculation, right? You basically take each isotope masses, multiply them by their corresponding fractional abundance, and then you add them up, and that gives you what we call the weighted average atomic mass. And it's called the weighted average because it takes into account the relative abundance of each element, of each isotope present for each element. All right? Okay, any questions about this? Any questions? Any questions? Okay, so let's see what we have here for you. Assignment for chapter 2. And well, I'm not sure. Let me see for you guys out there in Zoom. Let me see if I have published it. So let me. Here you go, sir. Let's see. Let's see. Okay. Okay, so and let me just say that I want you to focus on questions 1, 2, and 3. 1, 2, and 3. Questions 1, 2, and 3. In the meantime, let me take roll. Okay, so let's see here. Amo, Bassi is, I thought I saw his name. Yes, he's here. Bishop, Bragg, Caudill, Chestnut, Corwood, Erlinson, Gerard, Green, Leonard
Here.
is here. Muhammad Boy is here.
Clayton also just joined. You just called his name.
I'm sorry?
Chestnut also joined just now.
Oh, okay. Yeah, so I see his name. Yeah, okay. Spall, Suleiman, and Swistak. Swistak? Yes. Okay, so this is one. Which one you guys need help with? Oh, sorry? Zinc, yeah. Where's zinc? Yep. So the number of protons will be 30, and the number of neutrons will be what? 30? You sure about that? That? 35, exactly. I'm sorry? In an atom, yes, but not in an ion, which is the last one. But in a neutral atom, the number of protons and electrons will be equal. Okay, well, it depends. Is the ion positive or negative? If the ion is negative, that means that there's one more electron present compared to the number of protons present, right? For every negative charge, okay? So if there's a -1 charge, whatever the number of protons would be, you add one more to get the number of electrons. But if there's a positive charge, whatever the number of protons that is there, then you remove one electron or one from that number to get the number of electrons. Let me see, E or D? Well, it's an ion. It's also an isotope, but basically based on what you're given here, you know what the number of protons is? Chromium, where's chromium? Okay, chromium, 24. So 24 would go here, right? The number of neutrons, well, you have to subtract the 24 from the 52, right? So that gives you what? 28, all right? So the number of neutrons will be 28. So what do you think the number of electrons will be? No? Exactly, because it's positively charged. You have a +3. So that would be 24 minus 3, that gives you 21, and that's it. In the case of the iodide, charge, that means that to get the number of electrons, you add 1 to the number of protons. So, okay, so iodine is 53, right? So that tells you that the number of electrons will be what? Exactly. And what would be the number of neutrons? That would be what? Hold on 1 minute, yes? Sodium? No, that's sulfur. Sodium is Na. But I think you had the answer for, what was it? Number of neutrons, right? So you said what the answer was? I think that's right, because that would be 130 minus 53. Yeah, I think that's right. Yeah. So the number of neutrons would be 77 in the case of the iodide that is given there. All right, very good. I'm sorry? Exactly. You're absolutely right. You don't know what isotope it is because you don't know, they didn't give you the mass number, so therefore you cannot tell what the number of neutrons is. All right? Okay. Okay, number two says, okay, kind of similar to the one that we just did, right? They gave you this table, which gives you, okay, so they gave this table where they gave you the abundances of the different isotopes of magnesium 24, 25, and 26. And by the way, I don't think I said this, but whenever you see an isotope expressed this way, you can take this number to represent the mass number, all right? So they gave you the abundances of each of them, and they gave you the masses. And the masses, I should have put AMU here. So each of these masses would be expressed in AMU units. Okay, I'm not even going to try to write on this because my handwriting is terrible. So let me just ask you, how would you go about answering this question based on the example that I worked earlier? What would you do? I'm sorry? So in other words, if I get you right, you divide each of these by 100, right? Each of the percent abundance by 100. Right, and then what do you do with that? Multiply by the respective atomic mass. And then you do what next? You add them up, right? Now, when you're doing this, you have to be careful when it comes to rounding off, right? So for example, if you're multiplying 0.7870 by 23.98504, that result must be rounded off to 4 sig figs. And the same is true for the others, which I really wish I could explain or write to explain to you guys, but technology is not cooperating with me today.
Mr. Nestle,
Yep.
are you sharing your screen at all?
Oh, I thought I did.
I don't know. I don't know if it's me, but I just
Oh,
was asking.
yeah, apparently I didn't. I'm sorry. I apologize to you guys out there in Zoom. Let
That's
me do
okay.
that right now. I'm sorry about that. Really sorry. Okay. So, this is probably where we're working at. You guys need to speak. If you think that I'm not sharing my screen, please let me know. Um, you don't see it. Let's see, will this work? Okay, so, oh shoot, I like that. So their respective masses, you add them up, that's it. So any goal is done is zero. Zero. So again, variations. So eight, you know what? Yes. Right. So six, all right, so right, so let's take zero. Um, 17870, round it up for figures, and make the same figures. 10 point, well, not 10, 0.013, multiplied by 24.9854, 584, and the same thing for the manganese and phosphate. When you get those results, again, and, you have to run up the correct number of decimal places, which I'm not sure what it will be since I have not. Let me try to work this out here. 0.7870 times 3.985, so that should be 8.88, and then by 24.9854. So that should be rounded off to 2.531. And then the next number is 11.1, I'm sorry, 0.17 times 25.98259, and that should be rounded up to 2.902. So from the look of things, when you add them up, you should round off your answer to 2 decimal places. So if you guys have done that already, what was the answer you got? 24.30, okay. That sounds about right, because again, if you compare that to what you get for magnesium, what does it say here? 24.305, which is 24.31, so relatively close. So that's basically how that would, all right? Okay, let me get back to this here. The question says, copper is made up of 2 isotopes, and it gives you the 2 isotopes, copper 63 and copper 65. Each, given copper's atomic weight of 63.546, and that should be A mu, what is the percent abundance of each isotope? Now, this one is different from the previous one in that they're asking for the percent abundance of each isotope present. And it gives you the atomic masses of copper 63, copper 65, and the atomic weight that is given, that's assuming to be the weighted average atomic mass, right? So how would you go about doing this? How would you set this up? Let me, okay, so if you this, which is the from the periodic table for so the idea is that all the purchase. What? Let me have hand parts up here. The atomic mass would be equal to the percent abundance multiplied by the mass of each isotope, right? So let's say the percent abundance of 63 is X, that right? So that means if you take X, this mass here for copper 63, which is 62. Six the percent abundance like multiplied by 64.9. Um, 64.9. You is 3.46. So give an equation with two unknowns, right? And it's been a while since I've done algebra, but I do recall that you cannot solve an equation with two unknowns, right? In order for you to solve an equation with two unknowns, you're going to need two equations, right? So the question now becomes, what will be the other equation which relates x to y? And the hint to that is that we're going to assume that those are the two isotopes that exist only, right? So there's no other isotopes that exist. So if X represents the relative abundance of copper 63 and Y represents the relative abundance of copper 65, and those are the only two, then what's the relationship between X and Y? X plus Y is equal to what? 100% or 1, right? So X plus Y. I don't know what they call it. They call this simple equations. They call it something different nowadays, right? But basically, you have two equations with two unknowns, and now you should be able to solve for them because of the equation. So how do you solve for x and y? Now the equations with x and y. Any ideas? What do you mean? Subtract x from y? No, not subtract x from y. Oh, that makes sense. X equals to 1 minus y, right? And then that 1 minus y is where x is here, right? Okay, you know what? I'm going to leave you guys to do the rest because I'm really having difficulty writing with this tablet here. Don't know the reason why. I think it has to do with the Wi-Fi being slow. But I'm quite sure you're able to solve this problem from this step forward. All you have to do is put 1 minus y here, where x is, and then you solve for y. And then once you solve for y, you subtract y from 1, and that gives you x. And that is going to get the abundance of both copper 63, which is x, and copper 65, which is y. All right? If you have any questions, feel free to contact me in person or on Skype if you're encountering any difficulty while solving this problem. All right? Okay, so let me clear this. Let me here. So move on. And this is what he did was that he arranged the elements with this So the concept of having numbers is right? Mass. Simply our masses. So that's what you work with, right? Here's clear evidence. So many evidence. Here's so basically, here you explain that and when you repeat experiment, that has so that but he got now the thing about his table was that there were gaps that were left in the periodic table, which basically represent elements that were not found yet, right? So he did the trends just by following the trends, and he did have an understanding of how the electrons are arranged, which is actually what influences where different elements are located. So the trends are basically predictions about properties of certain elements based on the properties of elements, right? So, yes, I was saying it's able to make certain predictions or skills. It's to be located where it gets stuck. So just to table look like translated in English. This table this represents terms. The next slide shows the contrast between what and what was actually found as far as the properties that element is concerned. Now, the element that we're looking is during many of these predicted what these particular properties. Then so then in the set of different properties, and if you look at these properties side by side, you see how those observe what was verified both and then he also predicted the formulas of certain compounds that would combine this amount here. This one that he gave for this is actual formula identity. And you can say this relation. This one, what he could have predicted was that the melting point for chloride below degrees, and then the density of the chloride was predicted to be 1.9 grams per cm cube. And as you can see, the observed density is 1.887, right? So basically, and this is not the only example. The other example where there's a close relation between what is observed and what was predicted by Mendeleev before the element was discovered, right? So, of course, over the years, centuries, different elements were discovered, and now we arrive at the current table. Basically, the elements ranged in different colors and materials. So what categories? Like those elements to the left, these are metals, right? And each element you have the fundamental and you have the mass, right? Again, this mass number mass answer. Also, the mass number. For the sum of the number of protons is the weighted average mix of all the isotopes of that right? So we're going to say about the periodic table in more detail, because I want to get to some other topics such as before molecular of each element. In introductory chemistry, we get ratio elements compound, right? The molecular formula and the chemical formula are necessarily same thing as demonstrated here in this example. So in the case of hydrogen oxide, molecular formula is H2O, chemical formula is H2O. Hydrogen peroxide, the two atoms of hydrogen, one atom of oxygen. In the case of the the hydrogen. So in the case of octane, formula CH18 is empirical formula. The formula is CH18 for octane. Then what is the empirical formula? Well, remember the empirical formula gives you the simplest ratio. C4H what? 9, exactly. So that's the answer for here, all right? Okay, very good. Next thing on the top. In some cases, excuse me. So for example, for acid, right? This side right? The hydrogens, that carbon is also bonded to this carbon. That carbon is bonded to this oxygen, and one of these oxygen is bonded to this hydrogen. Especially for those of you working with these, what you'll find is that it affects molecules, three-dimensional shape molecule, right? So what you're going to find is that feel for the three-dimensional shape molecules, because based on that, you can tell whether a particular product will be formed or not formed, right? So what you're looking at here is what we call the ball and stick model, where the black spheres eventually are used to represent carbon, and white spheres represent hydrogens, and the red spheres in this case represents oxygens, right? So this is basically the ball and stick model for this single compound, acetic acid. This carbon is bonded to 3 hydrogen atoms. This carbon is also bonded to this carbon, which is doubly bonded to this oxygen, which is singly bonded to this oxygen, and then this oxygen is bonded to hydrogen. Right? So very important. Representing there are some inorganic molecules where ball and stick models would be useful for representation, but it's used a whole lot in organic chemistry. And then to the right, we see what is called a space filling model. Now, unless you're getting into graduate work, chemistry, medicinal chemistry, pharmacology, and so on, I don't think you'll encounter much of this. So this is important, however, because not only do we need to, in certain instances, know the three-dimensional shape, but you also need to know the relative sizes. This is particularly true when it comes to, for example, medicinal chemistry research, because a lot of drugs, the way they carry out their function or do their work is that the drug molecule has to be of a particular shape and size so as to fit into what is called an active site. And then when it fits into that active site, then it triggers whatever effect that the desired effect that you'd want, all right? So when you're dealing with high-level research, people have to be tailoring molecules so that it has the right shape and the right sizes so that it can basically fit into those active sites. And therefore, if it's a therapeutic drug or if it's something that is used to treat some sort of disease, then it can carry out that function, all right? So that's very important when it comes to that level of research. As I said, I don't anticipate, unless you're going to get into graduate work, I don't anticipate that you'll be using this space filling model very much. Okay, what time is it? Okay, we have enough time. Okay, so let's talk about in your introduction to chemistry. I know you spend a lot of time with my students in chemistry. Basically, about the rules for naming compounds, right? There's an organization known as IUCAP, stands for International Union of Pure and Applied Chemists, right? There's a division of that group which is responsible for coming up with rules for naming compounds, right? That's important because literally every year new compounds are made. Very often new compounds that are made will fit into that we're always such. So this organization has to meet in order to new rules on rules so as to accommodate compounds. All right. And I think they need every 5 years or something like that, right? For that purpose. So we're going to get into some of the rules for important. As stated here, we could have a specific equation, of course, that would be difficult to remember. So we do have rules which basically use the excessive repetition. If you know the rules, if you're given a name, you can write a couple of letters, correct? So there's for naming compounds. So the first type of compounds are what we call binary compounds, binary molecular compounds, right? Binary means is present per molecule. All right. So molecular means that elements must be all right for the let's say molecule. Now so that's what we get binary molecular compounds. Okay. Let's say that rules for naming these, right? First of all, the name consists of 2 words, right? The first word for naming these compounds will be the name that appears first in the formula, right? So that's the first word. Second word is then the name of the second element, all right? So for example, if the second element is oxygen, the name is oxide. If the second element is nitrogen, the name if the second element is sulfur, the name sulfide, and so on. All right, so that's what we mean by the second word. The name of the element is followed by the IDE. Another thing to take into account when naming molecular is that we define the name of the prefixes which indicates of each element present. So prefixes and then with 4, 2, 3, and so on. And we just like it. So it's the first one. Let me see that here. So it's 1 atom. More. If it's 2, it's like 3 tri, and so on. Right? But for all purposes, there. Right? So what comes up is which element comes first. Now you memorize this chart if you want to. I would recommend that, right? Basically, rule of thumb is that the element that's first on the left of the periodic table would be the one that is named first. In fact, that's the rule. Simply to look at the electronegative, one is less electronegative first, right? So, for example, if you have a compound forming between carbon and oxygen, right? Carbon is less electronegative than oxygen, so carbon will be first, then oxygen, right? Or there is that form between, let's say, oxygen and chlorine, chlorine first, then oxygen, right? So basically, the less electronegative element is indicated or named first. So, that. What is this question? It says, which element is named first? Exactly, because it's the less electronegative of the two elements, all right? Okay, so and the other thing focus on this here. And that is that the first element in the formula, the first element in the formula has only one atom. The first element in the formula has only one atom. That no prefixes are mentioned. The first element in the formula has one atom. Then no prefixes are mentioned. So therefore, you do not use prefix for that element. All right. The first element in the formula has only one atom. Prefixes are used for that element. All right. Let's see. That's important in the exams here. And there's another rule which has come to mind as well, which I don't have written down here. So you may want to write this down, right? If one of the two elements is hydrogen, we're still talking about binary molecular compounds. If one of the two elements is hydrogen, then no prefixes are used at all in that compound. If one of the two elements in the compound is hydrogen, then no prefixes are used at all right? Okay, so those are two important exceptions to the rules that we were just learning about. So, with what I just said, you can see why, for example, in this case of the first one here, is nitrogen monoxide, right? Now, if I didn't tell those exceptions, you'd be led to believe that you should get mononitrogen monoxide. But according to the example I just gave you, if the first atom or the first element has only one atom, we do not use any prefixes for that particular element, right? So that's the reason why this is called nitrogen oxide. That's the reason why it's called nitrogen dioxide, right? We do not use one of the nitrogen because the nitrogen is this compound, dinitrogen trioxide, di, because we have two nitrogens, right? So we use the prefix di for the nitrogen and then dioxide because we have three oxygens, right? Or this one, dinitrogen tetroxide, or this one, dinitrogen pentoxide, right? So as you can see, if you have more than one, right? 1, 2, 3 for the first element, you do need to use the prefixes. But if you have only one atom for the first element, no prefixes, all right? So we can see here, for example, this is called sulfur hexafluoride, right? Because again, there's only one atom of sulfur present, or this one I need fluoride. Now in this case here, you have P4O8. So the name of this compound is tetraphos, because we have phosphorus, because we have 4 phosphorus atoms. Then octoxide, because we have 8 oxygen atoms. Or this one, P4S9, tetraphosphorus monosulfide. This one, PS4O10, this is called tetraarsenic decoxide, all right? So basically you can see in these examples how the rules work. So, this one, it says the formula and name the compound for which each molecule contains 6 oxygen atoms and 4 phosphorus atoms. So they're telling you the composition of the molecule. 6 oxygen atoms, 4 phosphorus atoms. So let's do the formula first. The phosphorus compound, each element first. Right. So the formula would be, not the name, the formula first. P4O6, exactly. So the formula is P4O6, then it would be okay, you can say, according to IUPAC, you can say phosphorus hexoxide, or you can say tetraphosphorus hexaoxide. IUPAC actually recognizes both ways of naming compounds, right? So you can say hexaoxide or simply hexoxide. Both are correct. Okay. The next example, right? the molecular formula of phosphorus pentachloride. So what would be that formula? Phosphorus pentafluoride. Pentachloride, I'm sorry. Phosphorus pentachloride. PCl5, correct. And then the next one they're asking for the name of S2F10. Well, S2F10. Disulfur penta. Exactly. All right, very good. So based on what we have covered, you should now be able to do, in addition to complete number 3. Let me see here. Let me see here. Let me see here. Let me see here. Let me see. Yeah. Okay, you know what? Unfortunately, I don't have the questions in the correct order here. So let's see. Actually, okay, actually on the last page, question number 18. You guys, based on what we have just covered just now, I want you guys, when you get home, let me see what when you come back on Thursday, we'll see what you would have done with this. Last page, question number 18. These are all binary molecular compounds. So I want you to do those. If you have any questions again, please feel free to contact me concerning that, and I'm more than willing to help. I'm going to stop here for today, and I'll see you guys on Thursday. All right? You guys are there in Zoom, signing off now.